today?
Doing pretty good.
Good deal. So if I'm not mistaken, there was a request for me to work a problem using superposition and a problem using source transformation before I got into using nodal and mesh analysis. And so what I'm going to do is we're going to take one problem in the frequency domain and work it a number of different ways. So our problem of interest will be this guy. My pen thing will write. And I'm going to start with this circuit already in the frequency domain so that we really don't have to go through and figure out or convert it from the time domain to the frequency domain. So this will be our circuit. All of our resistors will be 1 ohm resistances. Our inductor will have an impedance of J 1 ohms, and our capacitor will have an impedance of J 1 ohms. We have a 6 angle 0 degrees volt source and a 2 angle 0 degrees amp source. So let's start things off by doing superposition. I feel like superposition would be one of the easier means by which to solve this circuit. And I guess I should identify the quantity that we're trying to find. So let's try to determine this phasor current I0 flowing through that middle 1 ohm resistor. So using the superposition method, we would turn one source on, leave the other source off, and then analyze the circuit. Since there's only 2 sources, we'll have to do this twice. So let's start with the voltage source on and current source off. So with our current source off, our circuit would look like this. Where, if you recall, we turn a current source off by open circuiting the current source because we want to make sure that the current that's being supplied by the source is 0 amps. All right, so here we have a number of different ways that we could approach this problem. I have something in mind that will involve rearranging the circuit slightly and then applying voltage division and then Ohm's law to get a result. But did anybody else have any suggestions on how we might approach this?
KVL?
So KVL, since if I were going to do KVL from here, I'd actually likely wind up doing mesh analysis. And I say that because I don't know the currents, and there's going to be more than one unknown current that we're dealing with. And if I were going to wind up writing multiple KVL equations, I probably would have just started with doing mesh analysis to begin with and wouldn't use superposition, if that makes any sense.
Yeah.
So any other suggestions? All right, so I'm going to redraw this circuit again because it's going to make it a little easier for me to look at this thing and kind of explain my process here. So hopefully you all understand what I'm doing, but if you don't, I'm happy to answer some questions. So what I'm going to do is I'm going to redraw this circuit, and I can say that because the 6-volt source, the J1 ohm inductor, and the 1 ohm resistor are all in series, I can change the order in which they show up in the circuit easily. They're all in series, so they're interchangeable. So I'm going to put my 6 angle 0 degrees volt source here. And then here is my 1 ohm resistor. Here's my, that's supposed to be J1, but didn't write particularly well. J1 ohm inductor. Now I have a 1 ohm resistor here. A 1 ohm resistor here. And a minus J1 ohm capacitor here. So before I start the analysis, is everybody on board with the change that I've made to the circuit?
Yes.
Okay, so, all right, so what I'm going to do now, let me put this on the other side here, doesn't particularly matter. I'm going to call this voltage V naught and solve for it using voltage division, which should be fairly straightforward, right? We have a voltage source connected to some impedances. So I could say that V naught is my 6 angle 0 degrees volt source multiplied by an impedance ratio, where the impedance that I'm trying to find the voltage drop over is that 1 ohm resistor in parallel with that 1 minus J1 ohm combination impedance on the right-hand branch. And in my denominator, I will have 1 plus J1 ohms in series with that combination. So I'm treating everything that I'm boxing here in red as a single equivalent impedance. Does that seem reasonable? Let's start there. Does anybody understand, or does anybody not understand how I can do this? I guess would be a better question.
That's voltage division, right?
Exactly right. So I'm just trying to find the voltage drop over that equivalent impedance. It's absolutely correct. So I'm treating that 1 ohms here as being in parallel with the combined impedance of 1 minus J1 ohms. And then I'm just using simple voltage division to get my result. And so if I do that, let's type it into our calculator and see what comes out. So I have 6 angle 0, and I'm going to have 1 minus, excuse me, yeah, 1 minus 1i in my numerator, and I'm going to have 2 minus 1i in my denominator of my first fraction. Then I have 1 plus 1i plus 1 minus 1i over 2 minus 1i. And I get 2.121 with an angle of negative 45 degrees volts. Did anybody else get something similar?
Yes, I did.
All right. So from this, just using good old Ohm's law, I naught prime will be V naught over 1 ohm, which in this case is going to be 2.121 with an angle of negative 45 degrees. Yes. Now I need to repeat with my current source on and my voltage source off. So with my voltage source off, I need to replace my voltage source with a short circuit. All right, so what it should look like would be, here's my 1 ohm resistor. Here's my J1 ohm inductor. Here's my 2 angle 0 degrees amp current source. My voltage source is a short circuit. 1 ohm resistor. 1 ohm resistor. Minus J1 ohm capacitor. And my quantity of interest is this guy, which I'm going to call I naught double prime. Any thoughts on how we might solve for that quantity I naught double prime?
Could we not just do current division?
We can absolutely do current division. That is what I believe to be the easiest method to use here. So employing current division, we're going to have I naught double prime would be 2 angle 0 degrees amps. And in our numerator, we're going to have 1 over 1 ohm. And in our denominator, we're going to have 1 over 1 plus J1 plus 1 over 1 ohm, plus 1 over 1 minus J1 ohms. So each of those three terms in the denominator represents the total impedance of each of the three different branches that are connected in parallel with our current source. So I can now just throw this guy into my calculator. 2 angle 0 multiplied by 1 over 1, or just 1, and then 1 over 1 plus 1i plus 1 plus 1 over 1 minus 1i, and I get 1 angle 0 degrees.
I'm getting an error every time, like whenever you did the voltage division, I was getting an error, and I'm just giving it to me again. I don't know what I'm doing wrong.
Does it say math error or?
It says stack error.
Okay, so you're using a Casio then, right?
Yes.
What I would like you to do is to just do this part right here in your calculator and tell me whether or not it gives you an error.
Just the denominator, or everything in parentheses.
The ratio there, so everything in parentheses.
Let's see. Yeah, it gives me a 1/2.
Okay, and then multiply that by 2.
Okay, answer times. Yeah. Okay.
Yeah. So it something about the multiplication of the fraction there sometimes causes Casio calculators to have a little bit of a fit. And so you just have to break it down into simpler calculations, which, you know, do the fraction part and then multiply it by the constant as a second step, and you're good to go. So,
Thank you.
yep. So we can put these two results together and find that our current of interest, I naught, would be I naught prime plus I naught double prime and when we add those two quantities, I get 2.915 with an angle of negative 30.964 degrees amperes. So that's one method by which that we could solve a circuit like this. So let's mix things up and do a source transformation method. All right, so let me scroll up here. I'm just going to copy this circuit. So in this circuit, I really only have one option with regards to a source transformation because I have my current source in parallel with an impedance of 1 plus J1 ohms, and that's the only one that I could potentially transform. So I'm going to do just that, right? So to be clear here, effectively what I'm doing, I'm going to draw a little terminal pair here. And I am saying that this network, my 2 angle 0 degrees amp source connected to be an inductor, although it really doesn't matter. J1 ohm, 1 ohm is electrically equivalent to a voltage source connected in series. I'm just going to use a generic impedance here. So I'm combining my resistor and inductor into a single thing that I'm calling just 1 plus J1 ohms, like so. So when doing a source transformation, what are the rules? I know that my impedance here has to stay the same, but how do I get that voltage?
Ohm's law.
Yeah, Ohm's law, exactly right. So I will literally just have 2 angle, sorry, that doesn't look like a very good 2. And it's not erasing, there we go. Amps times 1 plus J1 ohms, which would equivalently be 2 plus J2 volts. So these represent the exact same thing. So I'm going to redraw my circuit now that I know how the source transformation bit is going to work out. And so I'm going to have, make sure I give myself enough room. 2 plus J2 volts, excuse me, in series with my 1 plus J1 ohm impedance, in series with my 6 angle 0 degrees volt source. Here I have my 1 ohm resistor through which I'm trying to find that current I naught. Another 1 ohm resistor, and then a minus J1 ohm capacitor. So what could we do now?
You could add your voltage sources.
Okay. So I could combine my voltage sources together. I agree with that completely. They are of the same polarity, so they will just add together. 6 angle 0 is the same thing as 6 plus J0. So what I'm going to do is I'm going to erase this guy, short circuit it, and I'm going to add 6 to this, giving me an 8 plus J2 volt source on the left side. Is everybody okay with that source combination?
Yes, sir.
All right, so what might I do now? Any thoughts?
I mean, off the top of my head, I would say voltage division across that 1 ohm, but I mean, we've already done that.
Yeah, so that would definitely work. The approach that we tackled, this circuit is very similar to the one we just used superposition with the voltage source on and current source off, but we're having slightly different numbers. So 100% that process would work. But since I'm trying to work this guy using source transformation, what I'm going to do is I'm going to do another source transformation. So what I mean by that is I will replace my voltage source with a current source, having a current of 8 plus J2 volts over 1 plus J1 ohms. That would now be in parallel J1 ohm impedance which is in parallel with my 1 ohm resistor through which I'm trying to find that current I naught. And in parallel, and I'm just going to combine these guys for the sake of argument. Call this guy a 1 minus J1 ohm impedance over here. And I can now see that I can do current division very easily to find that quantity I, oh, sorry, there shouldn't be a prime there, I naught that I'm interested in. So the method that we used previously where we did voltage division and then used Ohm's law, absolutely okay. Gets us the result in 2 steps. Or another source transformation and then current division also gets us there in 2 steps. So it's really just whatever you're more comfortable doing, which is generally how most of these circuits will work out. So using current division, we'll have I naught will be equal to 8 plus J2 volts divided by 1 plus J1 ohms. And for those of you with Casio calculators that, tend to throw a little bit of a fit when you're doing complex math here, I would do this bit, store it as, say, variable A, and then do the ratio of the impedances, store that as variable B, and then just multiply those 2 variables together. So this will be 1 over 1 ohm, 1 over 1 plus J1, 1 over 1 ohm, and then 1 over 1 minus J1. And certainly hope that I get the same result as I just did when we worked the problem using superposition. So when I punch that into my calculator, I get 2.915 with an angle of negative 30.964 degrees amps. And if you'll give me just a moment, I'm going to scroll up and see whether that matched. And it does. So this is another means by which to analyze this particular circuit. Any questions about this particular methodology?
It really doesn't seem that much different from all we've done so far, except for the J's that you have to keep track of, honestly.
That is 100% correct. It is literally nothing different than what you have done thus far, except that now there are complex numbers to deal with. The circuit analysis techniques that we're using are the exact same DC circuit analysis techniques that we learned at the beginning of the quarter. So this stuff that we're dealing with today is really just a review. So you're not wrong. You're 100% correct.
What about the stuff with the power absorbed, the PL that we learned along with source transformation? Could you ask us a question like that on the final?
I will not ask you. So that is a fantastic question. We are going to cover steady state sinusoidal power analysis. And that is a little bit more involved. Like that's what we're going to start talking about on Tuesday, so tomorrow. So the power stuff, 100%. It's similar, but it's different enough to where we need to actually dedicate some time to it. And the reason why we have to actually sit there and dedicate some time to it is because we are fundamentally, when we calculate power, multiplying sinusoids. And that tends to mess things up a little bit. So our circuit analysis techniques for determining voltage and current and all that kind of good stuff, those are all absolutely fair game. We're going to do this problem using Nodal and this problem using Mesh in just a second, just to show you how to do those and how to set things up in your calculators, or excuse me, in your on Mathcad, should you choose to use Mathcad for your homework assignments. And I would very much encourage you to do that. But power, it isn't difficult, but it can be confusing. I can easily see how students become confused on it. So I'd like to kind of take our time and go through that over the next several days instead of just tacking it onto this stuff. All right, so would you guys prefer to do mesh analysis or nodal analysis next?
Nodal.
All right, nodal analysis. And while we are setting up this analysis, I'm going to apologize. I have to show you my terribly cluttered desktop so I can start opening Mathcad. All right, so since we're going to do nodal analysis, we need to identify our nodes, and I'm going to simplify that slightly. So we have our original circuit. I'm going to say that our nodes are as follows. If I can get this. So I'm going to consider this guy a node, this guy a node, and this guy a node. I am not considering this guy a node and this guy a node. And the reason for that, they are obviously nodes, but I am going to treat my 1 ohm in series with J1 ohms as a single impedance. Similarly, I'm going to treat my 1 ohms in series with a minus J1 ohms capacitor as a single impedance. So by just doing that simple impedance combination that I've just talked about, we effectively eliminate 2 nodes right off the bat. So I'm going to set this guy up using just these 3 nodes. So my question to you all is, which one should I choose to be my reference node?
Red.
Okay, so let's put it on bottom. There's my ground. So I'm going to call this guy VA. And let's call this guy here VB. So I have a supernode, right? I'm going to put a, let's use a color I haven't used. Kind of draw a little circle around it. Right? Anytime I have a voltage source, I have a supernode. So I'm going to have a voltage relationship. So I know that 6 angle 0 degrees volts, which is the voltage supplied by my source, will be equal to the nodal voltage at the positive polarity terminal, which is VB, minus the nodal voltage at the negative polarity terminal, which is VA. So that's one equation. My second equation will involve writing a Kirchhoff's current law equation at my supernode, right? Since my supernode doesn't contain ground, I'm going to add this current plus this current plus this current plus this current together and set them equal to 0. And that'll be 2 equations, 2 unknowns, and I'll be finished. So starting at node A, I will have VA divided by 1 plus J1 ohms. Then I will have minus 2 angle 0 degrees amps. The current flowing down through my 1 ohm resistor will just be VB over 1 ohms. And then the current flowing to the right will be VB divided by 1 minus J1 ohms. So now I'll need to solve this guy for VA, VB. So before we do that, are there any questions regarding how I got those two equations? Either my voltage relationship equation or my Kirchhoff's current law equation.
How can we like I see what you did there, like with the 1 ohm and the J1 on the left hand side. How can we just add those up and then say the VA over that is the total current?
We're treating it so. So you're asking why I don't say that I have some, let's call it VC here or VD here, right?
Yeah, because like every other analysis, we would do it like that.
So we could have combined resistors in parallel, but let's see what happens if we do nodal analysis at VC, just for the sake of argument here, right? So I'm going to do this in a slightly different fashion. I'm going to say that the current flowing in is the same as the current flowing out. So that would give me VA minus VC over J1 is equal to VC over 1, right?
Yeah.
Okay. So what I can do now is say that VA minus VC will be equal to J1 times VC. Does that make sense?
Yes.
All right, so now what I'm going to do is I'm going to put VA on one side. And so I have VA is equal to VC plus J1 VC. I'm going to factor out that common factor of VC, leaving me with 1 plus J1 ohms. So from this, VC is just VA divided by hold on, I think I made an algebraic mistake here real quick. Like the numbers are working right, but the okay, my units are garbage here. And the reason why my units are garbage here is when I multiplied by 1 ohms, I didn't carry that over. So let me just get rid of this ohm thing. So I get VC is VA over 1 plus J1. So it's effectively just a voltage division relationship, right?
Yeah, I see it now.
So effectively, the 5 steps that I did there are perfectly valid, but if I just treat that as a single equivalent impedance or a single equivalent resistance, if it were a DC circuit, I would still get the exact same result. All right. So Now I need to solve for these quantities, VA and VB. If there are no other questions, if there are, I'm happy to answer them. And to do that, I am going to use Mathcad because our calculators that are allowed to be used in this class cannot solve a system of equations that utilize complex numbers. So hopefully some of you guys are familiar with Mathcad. I'm going to use a solve block, which is how I will solve any system of equations. And I'm going to put in my guess values here. So I need to make a guess for my nodal voltage VA. And what I am going to do, I'm going to guess that it's 1 angle 0 degrees. So I do 1. And it's important that I use parentheses here and all this kind of stuff, because if I don't, it's also going to get weird real quick. So if we went under operators and we go down to where it says engineering, we have complex conjugate operation, a degree sign, the angle, and then a scaling thing. We're never going to use the scaling thing at all in this class. And to be honest, not entirely sure what it is. So since we're looking for angle, so we can input 1 angle 0, I noticed that there is a keyboard shortcut, Control-Shift-P all together gives me the angle operator. So that's how I'm going to be doing this from here on out. Now, if we mouse over those operators again, there is no keyboard shortcut for the degree symbol. To avoid having to constantly click the operator button and then come down here to do it, if you type in the letters DEG, it interprets that as an angle in degrees. So that's really all that we need to do. So I'm going to say that VA is 1 angle 0 degrees. And then the next thing that I'm going to do is also pretty important. So instead of implicitly multiplying, I'm going to explicitly multiply by the units of volts. The reason that I do that, Mathcad will interpret stuff in parentheses as being a function of other things. And it doesn't do that if I explicitly multiply. So that's why I'm doing it. I'm going to make my guess for VB. And I'm also going to say that it is 1 angle 0 degrees volts. Excuse me. And then now here in the constraints section, I get to start putting in my equations. So if I say something wrong, by all means, please let me know, because I'm trying to look at this guy without referring back to the work we did. So I should have VB minus VA is equal to 6 angle 0 degrees. That doesn't look like degrees. Volts as my first equation. And then I will have VA divided by 1 plus. So in Mathcad, we can't do J1 or it'll mess things up. So instead we do 1J. And then I need to make sure that I multiply this by the units of ohms. So to get ohms, I do Shift W to get the capital W, and then Control G. What the Control G does is change the last character to its Greek equivalent. So uppercase W is uppercase omega, lowercase w is lowercase omega, lowercase p is pi, lowercase t is tau. As you get more familiar with using Mathcad, you'll come up with all these shortcuts, but Control G to give you Greek letters is a pretty good one to know. So we have VA over 1 plus J1 minus 2 angle 0 degrees amps. Oops, excuse me. Plus VB over 1 ohm plus VB over 1 minus, 1J ohm. Oh, So it didn't like what I just did there because I forgot to do the units on the outside. And I set this equal to 0. And now, I think we talked about it in this class before, but I like to save all my answers in a matrix so that if I need to mathematically manipulate them later, I can. So I'm going to say that my matrix of VA and VB will be equal to, then I use the find function to solve my system. And it tells me that no solution was found. Interesting. All right, so it says no solution was found. Try changing the guess value or the value of the TOL or CTOL. I don't know what TOL and CTOL are, so I'm just going to come in here and I'm going to change this one to 2 and see what happens. And all of a sudden, it's able to solve it. If we click in here, so click one of my answers. Right now, they're displayed as a rectangular complex number. If I click on math formatting and I go to the bottom right-hand pull-down tab here for complex values, I can see that currently it's expressing my complex numbers in the format 1 plus 1i, meaning that it's rectangular format with I as the imaginary operator. The next one down is rectangular format with J as the imaginary operator, which is how we express complex numbers in rectangular form complex numbers in electrical engineering. Then I have polar form, where I have a magnitude and then an angle in pi radians. I have polar form with an angle expressed in radians. And then finally, I have polar form with an angle expressed in degrees. So that's what I'm going to do. So there we go. And now outside of my solve block, I'm going to say that my current I sub O is going to be what? Let's look back at our circuit here. What should I sub O be? Expressed in terms of our nodal voltages.
VB over or VB over 1, sorry.
Yeah, VB over 1 ohm. So let me VB over 1 ohm, and still gives me my answer in rectangular. 2.915 with an angle of negative 30.964 degrees, which is exactly what we got the other two methods we used. So it makes perfect sense that nodal analysis will work because all of our DC circuit analysis techniques are going to work. So any questions regarding using nodal analysis?
Is there a way I could do that without Mathcad?
Wolfram Alpha, that kind of stuff can do it, but there's not a way for you to do it with your calculator, unfortunately. So it will, solving a system of complex numbers, if you don't want to do it by hand using Kramer's method, which is absolutely doable, but is very tedious, involves the use of a computer algebra tool like this. All of you as Louisiana Tech College of Engineering and Science students have access to Mathcad for free. If you do not currently have Mathcad downloaded on your computer, send me an email and I will send you a link to the form that you fill out in order to get access to it. I'm happy to do so. If you choose to use a different computer algebra tool, you're well within your rights. Just know that if you don't use Mathcad, I probably can't help you because I only use Mathcad. Any other questions regarding this nodal analysis approach? All right, so we pop the keyboard off. And now let's talk about how we would apply this guy using mesh. Gonna be pretty straightforward. All right, so for doing mesh analysis, we obviously need to identify our meshes. So I'm going to call this guy down here mesh A, this guy here in the middle, mesh B, and this guy here, mesh C. Because I have an interior current source, I am going to have a super mesh. So I'm just going to outline where I'm going to write my Kirchhoff's voltage law equation for my super mesh. So I'm going to follow this purple path. I like to write my current relationship equations first. So for every current source, I should be able to write a current relationship equation. In this case, that should look like 2 angle 0 degrees amps will be equal to IB minus IA. Because IB is in the same direction as the current source as it flows through that middle branch, and IA is in the opposite direction. So that's why IB gets the positive sign and IA gets the negative sign. Now I'm going to write my Kirchhoff's voltage law equation. So I can see that I'm going to have 1 plus J1 ohms times my mesh current IA minus 6 angle 0 degrees volts plus 1 ohm times IB minus IC. Set this equal to 0. And then I'm going to write my Kirchhoff's voltage law equation around mesh C. So I will have 1 ohm times IC minus IB plus 1 minus J1 ohms times IC is equal to 0. And I can now solve this 3 equation, 3 unknown system. So before I pop back over to Mathcad and largely do what I just did a couple of minutes ago, are there any questions about how I wrote the current relationship equation or either of the Kirchhoff's voltage law equations?
No, sir.
All righty. So I'm just gonna try to scroll down here and then just solve block. And I'm going to do a similar thing. So I have IA. I'm going to guess that it has a value of 1 angle. Sorry, did not like something I just did. 1 angle 0 degrees amps. IB, I will guess, is 1 angle 0 degrees amps. And IC will be 1 angle 0 degrees. Oops, I hit that button too many times. Amps. In my constraint section, I'm going to start writing my equations. So gosh, let's see, that would be IB minus IA is equal to 2 angle, sorry, Control Shift P, angle 0 degrees amps. Then I have 1 plus J1 ohms times mesh current IA. Again, if I say something in one of these equations that doesn't sound right, please stop me. Minus 6 angle 0 degrees volts plus 1 ohm times IB minus IC is equal to 0. And my third equation should be, actually, there's a mistake up here. Because Mathcad will freak out, this should be 1 plus 1J. My apologies. 1 ohm times IC minus IB plus 1 minus 1J ohms times IC is equal to 0. I'm going to set up my little matrix. And I get those four quantities, which are all obviously in rectangular format. I'm going to change them to polar just because I prefer to work in polar. And our current of interest, I sub O, how would I write that in terms of my mesh currents?
Should be IB minus IC.
Absolutely correct. IB minus IC. .915 with an angle of negative 30.964 degrees amperes. So we have spent the last hour working this one problem 4 different ways. So we did it using superposition, then we solved it using source transformations, then we solved it using nodal analysis, and then we solved it using mesh analysis. So I really don't have anything else prepared for today. I'm happy to answer any questions if you do have them. I would like to talk to you for just a moment about the level of complexity of the circuits that you will ask to be solved on your exam. And to put it bluntly, the type of circuit that I just asked you about is as hard as it could be. Yeah, so Kevin Cobb asked, how would we do these on the test without Mathcad? Would we just have to use superposition source transformation? So I will never give you a circuit to solve that you can't solve without setting. So for exam 1, I told you guys I can't give you any circuits that have more than 3 equations and 3 unknowns, because you wouldn't be able to solve them using your calculators. For exam 3, I can't give you any circuits that would force you to use nodal or mesh analysis, period, right? At absolute most, if you're gonna set up a system of equations and solve for it, and I can't even really call this a system, would be a circuit where it's like 1 equation, 1 unknown. And then you could use, say, nodal analysis or something like that. And it's not even really nodal analysis, it's just Kirchhoff's current law and a little bit of algebra to solve it. Everything else will involve superposition, source transformation, all that kind of good stuff. So let me see if I can find a circuit real quick. Yeah, all right. So a circuit like this would absolutely be fair game. So let me draw something here. So let's say we have a voltage 120, angle negative 15 degrees volts. We have an impedance that is 40 plus J 20 ohms, like so. We have a current source, 6 angle 30 degrees. Give myself enough room. Amps. And then we have another impedance here. Let's call it 50 minus J 30 ohms. And I want to know this voltage drop. So by inspection here, we can pretty easily tell that we could work this guy using superposition and get the answer relatively quickly, right? I say that because if we have the voltage source on and the current source off, solving for that quantity Vx is just simple voltage division. And if we have the voltage source off and the current source on, solving for that quantity Vx, let's call it double prime in this case, would just involve Ohm's law. And then we would add those two results together and we would get our answer in 2 steps using superposition. But we could get our answer in 1 step by effectively doing nodal analysis, even though there's only one unknown nodal voltage. So what I mean by that is if I treat that as ground, this node right here represents my unknown voltage Vx. So I could say that Vx minus 120 angle negative 15 degrees volts divided by 40 plus J 20 ohms plus 6 angle 30 degrees amps plus Vx divided by 50 minus J 30 ohms is equal to 0. If I put this in the numerical solver of my TI calculator, it will give me an error because it can't solve that one equation, one unknown thing, because it has a complex number. But I would argue that I could break this thing down as Vx times 1 over 40 plus J 20 ohms plus 1 over 50 minus J 30 ohms will be equal to 120 angle negative 15 degrees volts divided by 40 plus J 20 ohms minus 6 angle 30 degrees amps. And therefore, Vx is just this quantity, which is a number that we can calculate, divided by this guy, which is also something that we can easily calculate. That is the hardest thing I can ask you to do on the test with regards to solving a system of equations is one equation and one unknown, which took me 3 lines of work. So I literally cannot ask you anything that will require you to apply nodal or mesh analysis that would wind up making you solve a system of more than one equation, one unknown, because you can't solve it, at least not in any sort of timely fashion. Mr. Cobb, did that help to answer your question at all?
Yes, sir.
Great. Any other questions or anything about this stuff? Do you guys want me to work more example problems, or do you want to call it a day? I'm happy either way.
I have one more question.
Sure.
Can you talk about how to differentiate between leading and lagging signals? 'Cause
Absolutely.
that confused me on the homework.
Okay. Why don't, do you happen to have the homework up so that you can literally tell me what your numbers are and we'll work your specific problem? If I can pop on my computer and pull it up.
Yeah, hold on. I'm going to it.
Sorry, the wrong mouse going. I want to say somebody asked me a question about homework 19 problem 2 as well over the weekend, and I don't think I answered it. So I can take some time to talk about that one too.
Me, I ended up figuring it out, but I got stuck on the same homework, but problem 3.
All right. So we're going to spend the next 20 minutes or so talking about homework 19, it appears, which is perfectly reasonable. Mr. Cobb, all right, you're first.
A good example was like number 1. That one was I just didn't. It just kept confusing me and tripping me up.
Okay, so let me get this. So homework number 19.1. So homework 19, problem 1. So we are told that V1 as a function of time is 63 cosine 120 IT minus 99 degrees. So I'm going to convert this to a phasor. I'm going to call that phasor V1, and it will have a value of 63 angle negative 99 degrees. For part A, on my screen, I have I1 of t is equal to 2.4 cosine 120 IT plus 118 degrees amps. So I'm going to call this guy I1A, and it would be 2.4 angle positive 118 amps. And I'm trying to decide if I want to do part B or part C or either of them. I mean, legitimately, this is actually enough to work with here. So, so let's just do part A. Part B would require you to change the sine function to a cosine function. So you do that by subtracting 90 degrees from the phase angle. Part C, you have a negative magnitude, so you need to convert that to a positive magnitude by either adding or subtracting 180 degrees. And then once you do that, it becomes the exact same thing as part A. So, actually, it shouldn't have an arrow there. I'm going to draw a plane here. where this is the 0 degrees, then we have 90, then we have plus or minus 180, and then we have negative 90 like so. I'm going to do V1 in red. So I have 63 angle negative 99. So it's going to be something like this, where this angle is negative 99 degrees. And then, oh, actually, let me write that as V1. And then I have my current as 2.4 angle 118. So 118 would be right about here. And this is I1. We are asked to find the angle by which I1 lags V1. So that means we start measuring from where V1 is. And because we want lagging, we go clockwise. So it's going to be this angle, which is 90 minus 9, so that's 81 degrees, plus this angle, where that is 180 minus 18, excuse me, 180 minus 118, 62 degrees. So we could say that V1 lags I1 by 81 degrees plus 62 degrees is equal to 143 degrees.
So when you're finding which, like if V1 lags I1, you would do clockwise. And if it's leading, if you're trying to find the angle it's leading by, you would go counterclockwise.
Exactly right. So when we go lagging is clockwise, leading is counterclockwise. Now I just looked up what WebWork considers to be the correct answer for this problem. And it says that the correct answer is negative 217 degrees. Well, 143 minus 360 is negative 217 degrees. This is where we get to what I talked about. WebWork doesn't know that 143 degrees and negative 217 degrees represent the exact same angle. So there is a distinct possibility that you can work the problem perfectly correct and WebWork won't like your answer. So all you need to do in that case is add 360 degrees, see if that works. If not, subtract 360 degrees, see if that works. One of those three things, your original thing, adding 360 or subtracting 360 will get you the correct answer. So the methodology of lagging going is measured going clockwise and leading is measured going counterclockwise is always correct. It's just whether or not WebWork accepts the answer that it comes up with. And I think that has something to do with the way that whoever wrote these questions, how they programmed it, which I can't program in Perl, so I can't throw too much shade at them, but it seems weird to me that the answer is negative 217 instead of positive 143. Did that help clarify things at all?
Yes, sir.
All right, so let me look at problem 2 just real quick. All right, so I'm going to do, I know that you, it was Mr. Gray, I think, that was talking, and I know that you said you figured out how to do problem 2, but I'm going to give you guys a much shorter way to do problem 2. Or potentially shorter way. So we are asked to find A, B, C, and phi if 33 cosine 100t minus 166 degrees minus 23 sine 100t plus 63 degrees is equal to A cosine 100t plus B sine 100t is equal to C cosine 100t plus B. All right, so doing this using trig identities is probably the way that this problem was intended, but it is absolutely not the way we're going to do it because that just takes too darn long. So instead, what I'm going to do is I'm going to take this thing right here and express it in terms of complex numbers. So the 33 cosine 100t minus 166 degrees, what is that going to be expressed effectively as a phasor? Should be 33 angle negative 166 degrees minus. So now you guys tell me how I convert 23 sine 100t plus 63 degrees to a phasor.
Shouldn't it be 23 angle 63, or do we need to get on both?
They need to both be cosine functions. If we're going to use a phasor representation, we have to deal with the cosine.
So then that would be what, 63 minus 90, I think.
Yeah, so 63 minus 90 is negative 27. My mental math is correct. So somebody please tell me what the answer will be if I do that math in polar form.
I got 49.851 with an angle of 178.74.
All right. So converting this phasor back to a cosine function would give us 49.851 cosine 100t plus 178.74 degrees. Let me did I write something wrong here? Hold on.
I think that's not the right answer.
I did 20 instead of 23, my bad.
Okay. All right. Sorry. All right. So let's scratch this. And scratch that. All right. So when we do 23, I think we get 52.570 with an angle of 177.32.
Yeah, I messed up. My bad.
Not a problem at all. Okay. Now, please tell me what the answer is. Convert that number to rectangular, please.
Negative 52.513. And then plus J 2.458.
All right. So it should be pretty obvious that this guy right here is C, and this guy right here is phi, or I guess we could call it C here and phi here. What is interesting is that this guy is A, and this guy is actually negative B. So the rectangular form gives us the expression of the sinusoid as a sum of sine functions with no phase angles, except that the sign on the sine part is flipped. And the reason that happens is because our trig identity says cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta, right? So this is the form we get adding the complex numbers and coming up with a polar representation. And this is the form we get with a rectangular representation, but our sign is wrong. And it's because of this trig identity. So I would be willing to bet that what we have just done there will probably take you 3 to 5 minutes, and using trig identities to suffer your way through it like we did that first problem. Remember that first example problem I worked where I tried to add two sinusoidal signals together and how much terrible trig and all that kind of crap that it involved? That's the way that you were, I think, intended to do this, but this method is, again, much, much easier. It's why we use complex numbers in electrical engineering, so that we don't have to use all that terrible trig. All right, now let's take a look at homework 19, problem 3. And I will tell you guys, extremely rarely, there will be maybe, I would say one student out of every 100 will randomly get numbers in this problem that make it literally impossible to follow the directions and get the right answer. And I'll tell you how you can tell whether or not that's you. So in this problem, we are told that a sine wave f of t is 0 and increasing at t is equal 1.2 milliseconds. And the succeeding positive maximum of 15 occurs at t is equal to 3.7 milliseconds. We are then asked to express the waveform in the following forms. C1 sine omega t plus some phase angle B. C2 cosine omega t plus some phase angle beta, and I need to put some constraints here. B is positive and small as possible. Beta is smallest possible magnitude. And then C is C3 cosine omega t plus C4 sine omega t. So going from the representation in B to the representation in C is literally the last problem that we worked, where we did it using complex numbers. So let's talk about how to get A, because A is, once we get A, the rest of this stuff is legitimately very trivial. Okay? So I'm going to draw a picture. So I think it can be helpful. This is not remotely going to be to scale, but that'll be okay. So this is our waveform f of t. What is the maximum value of the waveform according to the problem statement?
$15.
15. All right. So I'm going to say that my waveform has an amplitude of 15 because that's what it means when it says the maximum is 15. At t is equal to 1.2 milliseconds, which just for the sake of argument, I'm going to say is right here. The value is 0. And the positive maximum occurs at 3.7 milliseconds. Which means we have this. So what we have is exactly 1/4 of a sine wave described in word form or whatever, right? So what can we say about this guy? Well, t, actually, let me write this better. T over 4 is 3.7 milliseconds minus 1.2 milliseconds. So 3.7 minus 1.2. So from this, we know that this guy has a period of 10 milliseconds. Recall that omega is 2 pi over t. So if we have 2 pi over 10 times 10 to the minus 3. We have a frequency of 200 pi radians per second. So we know what C1 is. We know what omega is. Now we have to figure out what phi is. Well, if you look back at my notes where I talked about the review of sinusoids, we talked very specifically about what the phase angle is and how much it, the angle and all that kind of stuff that it represents a time shift either to the left or to the right. So when we consider this sine function, which we know, let me write this down to be 15 sine 200 pi t plus some phase angle phi, should phi be positive or negative here?
I would say positive.
So it will be negative because it's time shifted to the right. So a sine function should be 0 and increasing at t is equal to 0. But instead, it's 0 and increasing at t is equal to 1.2 milliseconds. So our phase angle should actually be negative because it's happening at the later point in time. So phi is going to be negative omega delta t. And what I'm considering delta t to be is this shift away from the origin. So for our case, that would be negative 200 pi radians per second times 1.2 milliseconds. And then we also need to multiply this guy by 180 degrees over pi radians. Because if we don't do that, we're going to get our angle in radians. So this is us forcing it to be in degrees. So negative 200 pi times 1.2 times 10 to the minus 3 seconds times 180 over pi gives us a phase angle of negative, 43.2 degrees. So our answer for part A is 15 sine 200 pi t minus 43.2 degrees. Now, if we look at our constraint here, it says that our phase angle should be positive and as small as possible. So right now, our phase angle is negative. So how do we make it positive and as small as possible?
We're just at 360.
Exactly right. Just add 360 degrees. So plus 360 would give us plus 316.8 degrees. And that is the answer to part A. Part B, we want to convert this to a cosine function where the magnitude of the angle is as small as possible. So what I would do is take this guy right here and convert it to a cosine. 15 cosine 200 pi t. And so now I need negative 43.2 minus 90 degrees. is negative 133.2 degrees. So as long as my angle is within negative 180 degrees to positive 180 degrees, it has the smallest possible magnitude. So this is our answer to part B. And then for part C, I would take the complex number 15 angle negative 133.2 and convert it to its rectangular format, where I would get negative 10.268 minus J 10.934, and recognize that this guy right here is C3, and this guy right here is negative C4. And I'm done.
That makes a lot more sense now.
Yeah, I don't want to say that the problem is worded poorly because I don't think it is, but it's asking you guys to do something that you've likely never even considered, which is to reconstruct a sine wave from 2 points. But we actually know enough about how sine waves function to be able to do that now. So. Any other questions regarding this homework set or anything else?